be a revolutionary technology. But the media is it's not always truthful. So I think accurate. So I think if you're really interested in quantum computing, I think you really should deserve to understand what is really the truth and what might be more hype, so to speak. So I'll explain today why quantum computing is interesting from a theoretical perspective, that is from the perspective of mathematics or computer science, independent of any possible implementation. So it doesn't matter if we're using, say, superconducting qubits or topological qubits, the theory behind it is still the same. And in the end, get a sense of what we might realistically achieve with quantum computers. So my story begins with, what is classical complexity theory and how the study of classical complexity theory came about. So, since mathematics has existed, people have, studied algorithms. We learn an algorithm in elementary school for doing arithmetic, and, there's other more complicated algorithms for different problems. So, for instance, Gauss, in his famous, work about number theory, wondered if there's a efficient algorithm for factoring integers. And, on the other hand, we have Galois on the right, who showed that there's no algorithm for solving polynomial equations in a certain model of computation. So this problem of complexity has been studied for a long time, stretching back to classical mathematics. So when complexity today sort of began with Hilbert and Turing, when mathematics had become more rigorous in the 20th century, and Hilbert was interested in asking if there's an automatic way for proving mathematical theorems. And Alan Turing, you might have heard about Turing from the popular media, and how he had a very unfortunate life. But his genius was that he was able to formalize the notion of computation, and ended up showing that Hilbert's answer. The answer to Hilbert's problem was actually no. There's no automatic way to prove mathematical theorems. So what did Turing contribute? He contributed the model of the Turing machine, which is an idealized model of a computer with its memory implemented as an infinite tape. And we also have the belief called the Church-Turing thesis, which states that everything that we can do in a computer in real life, say a Python program or any other computer that can be physically implemented, we can also do on this idealized model of a Turing machine. So this isn't a mathematical theorem. It's just a belief, but it can be turned into a mathematical theorem when looking at specific models of computation, such as things like recursive functions or the lambda calculus. It can be proven that these models of computation are equivalent to that of the model of computation given by the Turing machine. And so in some sense, this says that there's essentially one right way to define computability. So once we have the idea of computability, we can then look at the idea of efficient computation, which becomes very important when people start using computers in real life to solve practical problems. So one of these problems that was first studied is the matching problem, which essentially states, if you have a list of n people and who wants to work with whom, say represented by this graph on the right here, we want to find the maximum number of group of twos that can be formed from that list of people. So Jack Edmonds, shown on the left here, studied this matching problem and developed a polynomial time algorithm. So if you have a list of n people, this algorithm will terminate in n to the fourth steps. And in the same paper where he proposed this algorithm, he also proposed the idea that polynomial time computation is sort of the right definition of efficient computation. And you will use P to denote the class of problems with such a polynomial time algorithm. But then people then studied a lot of problems where they could not find polynomial time algorithms. So one of these problems is the traveling salesperson problem, which asks if given a list of n cities and the list of distances between them, and say number k, what is the length of the shortest path that visits every city exactly once? So an example is shown of a problem like that is shown in the figure below. So, and today, the best known algorithm for an exact solution has exponential time around 2 to the n time in the number of cities. So this is not a very efficient algorithm. However, this traveling salesperson problem does have the property that potential solutions can be verified quickly using short proofs. So let's say that I have a traveling salesperson problem, and someone else tells me what the answer to that problem might be. If I don't trust that person, I can still take their answer and check myself whether or not that is actually the correct answer or not in an efficient way. So to formalize this definition a bit more, problems where a potential answer can be checked using a short proof are called the problems in NP. And there are many such problems of this type. So people kept on finding these problems in NP where you can check the answer quickly, but you might not necessarily be able to come up with the answer quickly yourself. A series of work in the 1970s then provided an explanation for why this is the case by showing that these problems have the property that they are NP-complete. So what completeness means is that a polynomial time algorithm for one problem, say the traveling salesperson problem, would then imply that every problem in NP has a polynomial time algorithm. So under the assumption that P is not equal to NP, then every NP-complete problem must have algorithms that take super polynomial time. So this was one of the, I think this is one of the greatest insights in computer science, this notion of NP-completeness, because it provides at least a partial explanation for why many problems are difficult, or we believe them to be difficult to solve. And to this day, the P versus NP problem remains one of the, I think people recognize it as one of the most important problems in mathematics, and in fact is one of the Millennium Prize problems given by the Clay Mathematical Institute. So before I move on, are there any questions? Okay, so if not, I'll start to talk about how quantum computers fit into this story. So let's start with the very fundamentals of quantum computing, where quantum computing starts with the idea of qubits, where every qubit can be described by a unit vector, two-dimensional unit vector, where it is a superposition of two bits, 0 and 1. And there's this operation called measurement, where where, given any qubit with amplitudes alpha and beta, 0 is obtained with the norm of alpha squared, and 1 is obtained with the norm of beta squared. And the state of n qubits is then specified by a 2 to the n dimensional vector, where the state of n qubits is a superposition over all n-bit strings, and the same measurement rule is used to tell us what state this superposition collapses to after the measurement. So importantly, this superposition is fragile. So even though it might be supported on an exponentially many states, at any one time, to us, we can only observe one of them. So which makes sort of the design of quantum algorithms a very delicate process. So now that we have qubits, what can we do to qubits? We can apply quantum gates to qubits. And usually these quantum gates are 1 or 2 qubits, act on 1 or 2 qubits, and some examples are shown on this slide here, where we have different these poly operators and also the Hadamard gate. And so what do quantum circuits do? They implement these quantum operations such that the different interference patterns appear among the qubits, and one, as I just mentioned, so the design of quantum algorithms is very delicate, and we would want to implement quantum gates in such a way that whatever problem we're trying to solve, we will measure the correct answer at the end with high probability. So so this leads us to the definition of BQP problems. So we say that a problem is in BQP if one can solve it by a quantum circuit using a polynomial number of gates, such that after applying this sequence of quantum gates, the right answer is measured at the end with high probability. So I guess, sorry, I just looked at the Q&A, and there was a question about NP. So yes, it's certainly possible to prove specific problems are in NP. You just need to give a polynomial time verification algorithm. Okay, so I guess I answered it. Okay, so now back to quantum. So so BQP is now our definition of efficient quantum computation, just like how P was the definition of efficient classical computation. So the first thing that we want to observe is that any problem in BQP can be simulated by a classical algorithm in exponential time. So this means that if something that is not solvable by classical computers in exponential time, we definitely can't expect a quantum speedup for it. So that is, BQP can't solve uncomputable problems, for instance. However, there's this idea called the extended Church-Turing thesis that quantum computers present a significant challenge to. And what this extended Church-Turing thesis states is that every problem that we can compute on a computer in real life, we can do on a Turing machine with at most a polynomial slow down the runtime. So this means that if efficient quantum computing is possible, then either the extended Church-Turing thesis is wrong, which would be a very surprising possibility for computer scientists, or our beliefs are about the hardness of certain problems are wrong, which would also be a very surprising possibility. So I'll illustrate this with the example of Shor's algorithm and factoring that that some of you probably might have heard of. But before I get to Shor's algorithm, I'd like to firstly talk about a different problem. So this is the problem of Simon's problem. So this is one of the first examples of a problem where there is a quantum speedup. So in Simon's problem, we're given a particular function from n-bit strings to mapping to n-bit strings. And this function has the property that there is some string s such that f of x is equal to f of x plus x. So example, if n is equal to 2 and s is equal to 1, 1, then the function would be equal if f is evaluated at 0, 0 and 1, 1. And it would be the same when f is evaluated at 0, 1 or 1, 0. And a and b would be different. So, I give you this function f. I don't tell you what s is, but you would need to find this string s. So what Simon proved is that to solve Simon's problem, a quantum algorithm would need to evaluate f n times, but a classical randomized algorithm would need to evaluate f at least an exponentially many times. So 2 to the power of n over 2. So this problem is maybe a bit strange because I guess maybe it's unclear what the practical applications of a problem like this are. But it is a provably exponential separation. So it is something where we definitely can conclude that there's a difference between the quantum and the classical model of computation, especially since it's in this what computer scientists call the black box model, where we don't know anything about f other than this property. So f is an arbitrary function, but what we can't prove is that if somehow f has additional structure, we can't really say anything about the complexity in that case. So this this property that f of x is going to be is periodic actually turns out to be really important because instead of functions over bit strings, we can generalize to functions of the integers, and this problem is going to be called a period finding. So in period finding, we're given a function f from I guess 0 up to n minus 1. And furthermore, we have the property that f of x plus r is equal to f of x for some integer r. And so we call this integer r the period. And again, I give you this f, and you need to tell me what r is. So what Peter Shor did is that Peter Shor he looked at this proof of Simon's problem, and realized that you can actually generalize Simon's algorithm to this period finding problem. And he also realized that once you know how to do period finding, you can then factor integers. So I'll go through some of the details of this reduction now. And the punchline is that this is perhaps very surprising because we expect that factoring is difficult. A lot of our cryptography is based on the conjectured hardness of factoring. So maybe this is a bit alarming that that once large-scale quantum computers are built, much of modern cryptography could be affected by that. So So let me now explain why period finding is important. So let's say that you have an integer n and some number a less than n. And we assume that a and n are co-prime. That is, the greatest common divisor is equal to 1. So we're given this function f of x equals a to the power of x modulo n. So so for those who haven't seen this mod notation before, this is the remainder of a to the x when divided by n. So this function has some period r, which must satisfy this equation that a to the power of r mod n is equal to 1. So an example with a equals 2 and n equals 15 is the following. So when we evaluate it at 1, we get 2, f of t is equal to 4, f of 3 is equal to 8, f of 4 is equal to 1, f of 5 is equal to 2, and we can repeat this and conclude that the period is equal to 4. So now at this point, we found the period. So, and indeed 15 is equal to 2 to the 4 minus 1. But now we can factor this expression because it's a difference of squares. So it then factors into 2 to the 2 minus 1 times 2 to the 2 plus 1, which are exactly the factors of 15, 3 times 5. So therefore, if we can find the period of this function, and furthermore, the period is an even number, then once we have this difference of squares factorization, and we can try to use it to factor this number n. And this there's some additional conditions on the number n to guarantee that you have such a factorization, but maybe it's a bit too technical for the purposes of this talk. So this is exactly how Shor's algorithm works. So sorry, maybe I should ask if there's any questions about this slide first before I move on. Okay, so if not, I think I'll continue. So what Shor observed is that by generalizing Simon's algorithm, this leads to a efficient quantum algorithm for period finding of this function f that was just mentioned here. So I won't go too much into the technical details, but for those who are interested, this uses something that's known as the quantum Fourier transform. So so you can use this quantum Fourier transform to find this period. And once you have the period, you can then factor your integer n using the procedure I described on the previous slide. So then the analysis when we put everything together, by analyzing, how often the period is going to be even and all the details I mentioned previously, this analysis will imply that on n-bit integers, you'll need approximately n to the third power of quantum operations to factor this number. On the other hand, the best known classical factoring algorithm, which is called the number field sieve, will take exponential time. And as I mentioned, if we believe that cryptography is safe, such as algorithms such as the RSA algorithm or the Diffie-Hellman key exchange algorithm, these cryptographic algorithms work because we assume that if we assume and that factoring is hard. Sorry, let me say this again. So these cryptographic algorithms are secure if we assume that there's no polynomial time factoring algorithm. So when Shor published his algorithm, this made a lot of people very interested in quantum computing, because I guess maybe there's an alarmist aspect to it. If you're working in security, but I think it's also good in the sense that it shows that quantum computers don't just solve physical problems, problems that the physicists are interested in. It can actually solve a lot more problems than that. So I think this is the result that that really got mathematicians and other computer scientists interested in the area. And just to maybe be reassuring, we do, people have estimated, how long it takes to implement Shor's algorithm at a level needed to break current cryptography, and at the moment, we still need millions of qubits. So for the time being, we can still use things like RSA. So I guess there's a question about the quantum Fourier transform. So it is, the same as the discrete Fourier transformation. So maybe, I guess there's a continuous Fourier transformation and a discrete Fourier transformation. So we can look, so it is an implementation of the discrete Fourier transformation using, that can take the Fourier transform of a function defined on, I guess, n values in log n operations. So it is really the same, except the quantum version is a lot more efficient. Yep, I hope this answers the question. So I think this is a good time to pause to ask if anyone else has questions, or is there any questions in the chat? Okay. So we've just went through, Shor's algorithm and, sort of giving you a high level idea of how it works. So it uses this quantum algorithm for period finding, and uses the period to get the factors. And so, other kinds of problems in number theory, can also be solved using quantum algorithms. So for example, Pell's equation, which is finding an integer solution of this equation, x squared minus dy squared equals 1. Elliptic curve cryptography is also another area where there's quantum algorithms for breaking these kinds of crypto systems. And you'll sort of notice a pattern that many of these problems that quantum algorithms are good at have this sort of algebraic or number theoretic structure to them. Other examples that are maybe a bit more unusual are approximating this polynomial called the Jones polynomial. And this has applications in other areas of mathematics, such as knot theory, and also is studied in quantum field theory. And there is also naturally the problem of Hamiltonian simulation, which is maybe something that more physicists or engineers care about, where given some Hamiltonian H and some initial state psi of 0, we'd like to compute the solution to the Schrodinger equation given by e to the exponential of IHT times, this initial state. So, all of these problems, are have efficient quantum algorithms. We even believe that, some of these problems are BQP complete. But for none of these problems we've really found an efficient classical algorithm for. So this shows us that for these sorts of algebraic problems or physically motivated problems, we can't expect quantum speedups. However, can we expect quantum speedups for these NP-complete problems that we talked about earlier, like the traveling salesperson problem, or other if you maybe know a bit more about NP-completeness, you also know that problems like graph coloring are NP-complete, or the clique problem is NP-complete. So we know that there is some speed up because of this an algorithm called Grover search, but the speed up is probably not exponentially large. And this is due to the following theorem proved by Bennett, Bernstein, Brassard, Vazirani in 1997, which states that well, given the function from 0, 1 to the n to where each bit is assigned 0 or 1, it's still going to take exponentially many steps for a quantum algorithm to find an element where f of x is equal to 1, or return that it doesn't exist. So this essentially shows that this Grover search algorithm that was developed is the best algorithm for quantum search, if we only given this condition here. So this shows us that, well, probably for NP-complete problems, we can't have exponential speedups. Only polynomial or quadratic speedups are possible for NP-complete problems, because, well, I guess many NP-complete problems can be phrased into this form. Has this form of finding an element where f of x is equal to 1 or not. However, a direction of current research that many people are actively looking into is, I guess, lots of different quantum heuristics for NP-complete problems. It could still be the case for special cases. They could be faster than classical algorithms, and some of the things that you might have heard of in this direction are things called the variational quantum eigensolver, which I think someone else will give a talk on, and another algorithm called QAOA, the quantum approximate optimization algorithm. And comparing these algorithms to classical algorithms is the direction of current research. So in the last part of my talk, I think I'll also talk about some open problems that I think are very interesting. So I think one direction that's really interesting is the relationship between physics and complexity. One of the reasons why people have a lot of faith in quantum computers is their ability to natively simulate the quantum physics. So one thing you can try to do is ask, let's say that you have a superconductor and it has some quantum state. how complex what do you need of a description does it have? And right, sorry. Right. So let's say that you have, some sort of equations or some sort of Hamiltonian describing a superconductor, and you want to find its ground state. How complex is doing that? And this is part of the theory of QMA completeness, which is an extension of the theory of NP-Completeness previously described. So if we can show, we can show a lot of these problems are in this complexity class of QMA, which is kind of like NP except for quantum computers. So so this shows that this maybe contradicts some physical intuition that I guess depending on how you think about physical systems, you might think that finding ground states are easy or not. But I think this is an interesting connection between physics and complexity. Another direction that you might have heard about is this area about interactive models. So so in an interactive model, imagine that you yourself, you're a classical polynomial time verifier, but you can talk to two quantum computers that we assume have unlimited power. So you have a problem in mind, and you want to use these two quantum devices to solve a problem. And you want to be sure that the answer is correct. But your resources are limited and you only have polynomial time. Well, it turns out that yourself being polynomial time isn't really a limitation. Because just earlier this year, it was shown that this interactive model contains all computable problems. And the fact that it does also resolves long-standing open problems in pure mathematics too. So so this is a very exciting definition of direction of current research, and involves is something that I guess many people are looking into right now. And let me just say that I think these sort of interactive models are also motivated by cryptography considerations. And additionally, so far, we assume that our quantum computers don't have any noise. They work perfectly. We know that's not the case in the real world. So something that people are looking into right now are, how can we, extend a lot of these results about quantum advantage and the power of quantum computers over classical computers when we add in the fact that real life quantum computers will have some sort of noise in them. And finally, quite frankly, I've given some examples where we conjecture that there's a quantum speedup, but for near-term applications and for problems that other areas of computer science might care about, like machine learning, what kind of quantum speedups can be achieved in those areas is, I think, something that a lot of people are thinking about. You might have heard of this this algorithm by Yuan Tang, who was very famously showed that one of the conjectured quantum speedups actually is false. There is actually an efficient classical algorithm for a particular machine learning problem. And so, this makes the area very exciting because I guess you might, I guess there's a lot of open problems because of this, I think. So to conclude my talk, so we've talked about computational complexity theory. It's a branch of computer science and mathematics that rigorously studies the power and limitations of different algorithms. And we can apply complexity theory to both classical algorithms and quantum algorithms. Quantum algorithms work by creating interference patterns among the qubits in a clever way, such that the right answer is measured at the end with high probability. Efficient quantum algorithms likely cannot solve NP-complete problems. You might have heard that they can in the media, but this is false, or believed to be false. But many other interesting speedups are possible, like like Shor's algorithm and other problems dealing with algebraic problems. And there's a lot of open questions about the power and limitation of quantum algorithms. People are very excited about quantum computing right now, and this is probably why you're listening to me, because we're seeing the first generation of quantum devices are currently being built with, say, 50 or 60 qubits. This is a level that is not believed to be classically simulated, but I guess it's still not at a powerful enough level where we can do things like Shor's algorithm. So I think there's a lot of interesting work to see what kind of power the first generation of quantum devices can bring. But in my view, I think the theoretical perspective, thinking about what could happen if once we have millions of qubits, still provides a very valuable perspective. Large scale quantum computing might not happen in my lifetime. And, there's still a lot of skepticism about the field, whether or not quantum computers, can scale up to that large. And I think the theoretical perspective could clarify a lot of things, whether or not could clarify a lot of these engineering challenges in the end. And I think more importantly, quantum computing is valuable as a field because a lot of the things that have been studied and applied to quantum computing, at first they've been applied to solve a quantum computing problem, but then maybe a few years afterwards, they've been applied to solve unrelated problems in physics, computer science, and other areas of mathematics. So I think for this reason, it's still very valuable to think about. So even if we never build a practical quantum computer, I think it's valuable for this reason that quantum computing could be a bridge between different areas of science and could inspire many collaborations between different scientists. Yeah, thank you for listening. I know that if you're not that interested in theory, being in a theory class could feel like what I've shown on the comic.
All right, so thank you so much for your talk. It was very nice to learn about all the different ideas in quantum complexity theory, and I hope a lot of you in the audience have gained a lot of knowledge from this talk. And so we're gonna start our question and Q&A sections now, and if there's any questions, so just type in the chat or shoot in the Q&A session. So we'll be here for I think around 10 minutes, but so yeah, we'll be open to take any questions.
Right. So I guess I see a question from Mataba. So Right. So so my research is in, I guess I'm really focusing on two areas right now in theoretical computer science. So the first is I guess quantum complexity theory. I'm looking at this theory of QMA completeness, which is like the theory of NP-Completeness, except applied to quantum computers. I'm trying to look at what kind of problems are QMA complete, and show what kind of limitations QMA has. And I'm also thinking a bit about another area called proof complexity, which is I guess how to describe it. Right, which is I guess more related to not really related to quantum, but is more related to things like mathematical logic. So I think I'm focusing mainly on those two things right now. Right, exactly. I guess everyone wants to solve P versus NP, and I guess there's I'm looking at.
Any other questions from the audience? Well, seems like we have a silent crowd. But that's okay. That's probably just say that you're pretty comprehensive talk. So yeah, so I think if there's no more questions, I think we'll probably end early today. But yeah, so I think Adrian, if you're willing to share your your email or some context you're willing to, maybe someone can if they have some private question they can shoot it up. But if not, no pressure. So yeah, so thank you so much for showing up for today's event. So there will be another one. So as Adrian said before, there will be another one on Q, like very technical detail on BQE. So if you want to learn about that, so please join tomorrow at the same time. So yeah, so thank you so much for showing up. Yeah, thank you. Have a wonderful evening. Yeah, that was it. Thank you.
Okay, so I guess maybe once you stop the recording, we can chat a bit more or something like that.
Yeah, for sure.